Okay, so let's look at some equation, derive VOT and V in T equation here. You can see this VOT changes at the end of by one page here, right? In the previous during by two page, VOT doesn't change. So I will set timing convention this way, the same way as in inverting case. Okay. So this is my T equal NT. This equal is T equal n minus 1T. Okay. And then my by two base is here. So here, so this one is T equal n minus 0.5T. Okay. Yeah. So this added charge. Oh. Yeah, this when is this V in charge sampled? Yeah, it was sampled during by two page, right? So it was sampled here. So this added charge is actually C1 V in n minus 0.5T, right? Because it was sampled there. This V in T may change with the time. Yeah, this signal change with the time. That this C1 charge was sampled at the end of by two base, right? It was charged there, and then it was transferred to C2 at the end of by one base. Okay. So by comparing Q2 between those two time points, the Q2 charge is incremented by this amount, right? Now then we can derive equation. So Q2 charge, so I define my Q2 that way. Then Q2 charge is C2VO, see here is NT minus 1.65, C2VO n minus 1T minus 1.65 was changed by C1 V in n minus 0.5. Okay, this is my equation, all right? So let's just see, is it right? Oh, maybe V in minus 1.65 or something like that. So I will drop all those 1.65 because that is a DC term. So I will delete out all those things and then we can derive equations. Okay, the non-inverting integrator, switch capacitor integrator, the equation was V C2VO NT equals C2VO n minus 1T plus C1 V in n minus 0.5T. Okay? So it is, I want to use G transform to describe this one. It is difficult to use a Laplace transform here. Laplace. There is some time shift here, right? Time shift. Those are some time shifting. If you compare those two, it is a delayed by t. So if my Laplace transform of ft is fs, then if my time shifted version, so if I have those things in equations, it is very difficult to solve, right? So this is called the discrete time system. In the switched capacitor filter, we care about the binary values at the end of by one page, right? We don't care about the transient values. So it's like similar to sampling. It is a discrete time system. So for the discrete time system, we use just Laplace G transform. G transform is much better. Yeah, for example, this is Fz. Yeah, this should be some different value. Eh? Then, if I have a shifted value, then this is Fz G minus 1. So it's much easy to handle this G minus 1 over Z, right? Because this is we can use algebraic equation. Algebraic equation. Here we need a transcendental equation, difficult to solve. So if I apply Laplace transform this equation, this is G transform. C1, this is actually C1. C1 okay. So we'll use a G transform. Where is my G transform? Okay. Yeah, non-inverting integrator. Yeah, the equation was like that, right? Okay, so I can write my transfer function easily, right? C2. Okay, so this is my G-domain transfer function. So, you know, this in a Laplace transform, this is my integrator, right? Integrator. But in the G-domain, this is my integrator. So if you look at this one, say this is the same as this one. If Z is smaller than 1, you know, they are the same equation. So you can say this is, for example, say this is just a sum of, in the time domain, this is just ft minus t, ft minus 2t, ft minus 3t, something like that. So, you know, this is just adding a series of time-varying signal. This is nothing but integration, right? They're adding together. So you can see this is integration. Question? No? Okay, how come there is no question? Let me ask, who is 이경준? Who is 이경준? Yeah, any question? No? Are you familiar with the switch capacitors? I mean this G domain transform. Then you have to ask question. Huh? No? G? Let's see. Oh, is it right? Let me see. G. This should be. This delayed. Let me see. The ratio. This ratio. This is the. This should be less than 1. Oh, that's a little bit weird. Eh? Is it true? C delaying operator. Let's just see. Oh, looks like you're right? So I'm multiplying this one, right? Every time. So this should be true. Then this should be this way. Is it region of convergence? That is called the region of convergence. So let me check. Integration is okay. That's a region of convergence, which is same. Oh yeah, you're right. Unit step. Actually, this is similar to unit step, right? Integration transfer function is G domain transform over this unit step. Each region of convergence is larger than 1. Okay. Okay. So yeah. So G domain. So we'll use G domain transform in this switch capacitor filter analysis. So G domain transform is this G is defined. This is actually time domain, BIT. So yeah. So G domain transform is we just sample VIT. Yeah, this is time domain. So for example, so this is my VIT, and then we just sample this value. Yeah, this for example, this is k equals 0 here, k equal 1 here. See, k equal 1 means this t equal kt. Okay. So this is t equal kt. So I just sample those values and then multiply G2 minus K. So I multiply this one by G2 minus 0, multiply this one, G2 minus 1, G2 minus 2, this one, G2 minus K, and then add them together. Okay, that's a G transform. Yeah, if you have a unit step, see, for example, my VIT is a unit step. Say, what's my G transform? T, and then, see, this equals 0, 1, this is a T equals 0. So I will sample those points, right? Even T equals 0, this is my definition 1. Yeah, T, 2T, 3T. So by using that definition, so this is a sigma K equals 0, because negative is all 0. Then infinity VI KT times G to the minus K, right? This thing all 1, so this is nothing but G to the minus K, right? So it is okay. Same as this unit step. The G domain transfer function is the same as transfer function of integrator. Okay. Yeah, what's a delta? When BIT is a delta, this is actually impulse input, right? This is called the impulse input. Yeah, this one is delta t is only 1 and all 0, right? All 0. That's a delta, right? So it's easy. My VIG is definition k equals 0 minus infinity, infinity, VIKT, g to the minus k. So this is only 1 at the k equals 0, right? K equals 0. So this is nothing but 1. Oh yeah, it's the same, right? If I have a Laplace transform, this one is only 1, right? Same. Yeah, so you can derive a G-domain transfer function. So usually, so we are talking about the region of convergence. For the transfer function, see, we are talking about the transfer function. For the transfer function, so we are not talking about the G-domain representation of a signal. We are talking about the transfer function. In a S-domain transfer function is stable if all poles located in a left-hand side of a plane like this. So this is sigma j omega. If a pole is located here, the real part of a pole is negative. It is stable, right? Similarly, in the G-domain, the G-domain transfer function is stable if all poles are located inside the unit circle. Okay? So you can see this part. Oops. You can see this part of S-domain region is mapped into this inside the unit circle because G equal exponential ST, right? Then this G equal exponential sigma plus J omega T. So this sigma is the real part, right? This is my sigma. So this is exponential sigma T times exponential J omega T, right? So, this thing is only exponential sigma T, right? Because this is 1. If sigma is negative, should be 1. Right? Okay. So this plane, which is sigma negative, is mapped into inside of a unit circle. Okay, question? Nope. Okay, we want to derive a transfer function. I think we already derived it, right? During we just stick to this one, this time convention. So this is n minus 1t. This is nt, right? So here, because my Bouillot changes during by one phase, I want to make the integer times t time the end point of by one. Okay. So here, see, we already know the charge here. This Q2 charge is only C2 times VO t minus 1.65, right? Yeah, I just deleted 1.65. Okay, my C2 charge will change. Yeah, what changed that charge? So that's a charge dumped by this V in, right? So at the same time point, which is C1 V in NT, okay? Not n minus 0.5, okay? So I can derive a G-domain transfer function. So C2 VOZ equals C2 VOZ G minus 1 minus C1 VIZ. Okay. So my transfer function, which is ratio of VO and VI, is only C1 over C2, that integration operation. Okay. So we use this one. Any question? Okay, let's start here.